Hi YouTube. Today I will again simulate the spread of COVID-19 using the SEIR model implemented on a keystroke programmable calculator. In the previous video I used the HP35S, which uses reverse Polish notation, but today I'll use the much older and slower but quite quaint TI-66 programmable calculator. This uses the algebraic operating system notation, which means you enter in your operations, your equations in the way you would write it on a piece of paper, as opposed to numbers first and then operator. Number, operator, number, order of operations, and so on. I'll explain the SEIR model again. SEIR is susceptible, exposed, infected, and recovered. Now I have the same equations I showed in the previous video, but I want to explain why these differential equations, ds, dt, and so on, come from the model. In order to go from susceptible to exposed, susceptible individuals interact with infected individuals with a coefficient beta. Negative beta times SI is then ds dt because there's susceptible individuals lost at that rate dependent on the number of susceptible individuals at a given time and the number of infected individuals. The number of exposed individuals correspondingly increases at that rate, and it decreases at the rate alpha E, where alpha is 1 over the incubation period. So once the incubation period is passed, those individuals become officially infected and no longer exposed. For change in infected over unit time, then it's alpha times E minus gamma times I. That's the incubation, or excuse me, not incubation period, the infectious period. The time during which these individuals can spread the disease to susceptible individuals. So we saw alpha times E for going from E to I, and then for I, it's gained at the rate alpha times E minus gamma times I. Finally, recovered changes in time at that rate 1 over the infectious period times infected. After that time, these individuals, we assume here, are recovered. Okay, so the way I'll be modeling this is through the semi-implicit Euler method, where I take starting conditions and then add in ds, calculated here from those differential equations times the dt parameter, and I'll go through 400 iterations here. These are the parameters I'm going to enter in the calculator, and it's 400 iterations because I'm going to stop at 40 days with a dt of 0.1 days. Alpha, which is 1 over the incubation period for COVID-19, is 1 over 5 days, so 0.2. Beta, the contact rate for converting susceptible into exposed, is 1.75. This comes from the R0 value and the infectious period. So it's known that infectious period is 2 days. 1 over 2 days is 0.5 for gamma. 0.5 times 3.5 then gives the contact rate, or beta, converted from R0. R0 is the number of individuals that an infected person would make infected. So say if I'm infected and I'm interacting with other people in a normal way, on average 3.5 more people would become infected later. And my starting conditions will be 99.99% of the population susceptible, 0.01% exposed, none infected, and none recovered. So I'm going to go ahead now and enter it into this calculator. I have a listing in the description, but for now I'm going to enter in the starting values for those parameters in these registers 0, 1 through 10. Okay, so starting susceptible, 0.9999. I'll store in 0, 1. Then starting exposed, 1 in 10,000, I will store in 0, 2. And 0, I'll store in 0, 3. 0 in 0, 4 for infected and recovered. And now for the different coefficients. 0.2, I will store in 05, 1.75, I'm going to store in 06, and 0.5 I'll store in 07. Finally, for this simulation, I'm going to start with no social distancing, a rho coefficient of 1. Later on, I'll do that being the simulation with the social distancing coefficient of 0.8. So I'll go ahead and do 1 store 0.8. And now for dt and tmax, 0.1 store 0.9 and 40 store 1.0. Now I'll just briefly show you the program. I'll press RST to go to the top of the stack and the Learn button, and I'll show you the first few steps in the program. It's label A, so I'll press A to run with those given parameters, what's stored in those 10 registers. Recall 10 divide by 9, that's to get the number of steps. Store that in 0, 0, the loop counter, and then go through the differential equations. A lot of recalling and multiplying and a little bit of register arithmetic, where you take whatever's in the X register and instead of putting it in another numbered register, you multiply it or add it or subtract or divide by what's there. Okay, so I'll go back, learn again, RST, 0, CE, clear the entry, clear the X register, and let's run this thing. Okay, after a whopping 55 minutes, our simulation's finally done and we have an answer. Keep in mind this is a calculator from 1983 that runs at an agonizingly slow 220 kilohertz, half the speed of its predecessors TI-68 and TI-59. But anyway, now that we have the simulation complete, let's take a look at the answer. I'll first recall the register 01, and that's our proportion susceptible after 40 days, which is about 24%. Now let's look at exposed in 02. About 25.4% that are exposed. 03, 10% that are infected, and let's see how many recovered. 40.7% recovered, the most by far. This was with no social distancing. Now let's redo the simulation with a 0.8 rho coefficient indicating 80% as much contact, so some degree of social distancing in our population. To do that, I'll go back through and re-enter the parameters in the registers. I'll store 0.9999 into 01, and then 0.0001 into 02, 0 into 03, and 0 into 04. Now what will be different now is 07. So if I recall 07, oh excuse me, not 07. If I recall 08, that was 1. Now we're going to change that row parameter to 0.8. So CE, CLR, 0.8, still 08. Okay, so quick recall now. Call 05, call 06, 1.75, that's good. Call 07, 0.5, that's good. And recall 08. A couple more, 09, 0.1 days for the DT, and 40 days for final T. Okay, so I think we should be good now. I'll check one last time, third time's the charm, and also make sure that I entered in the initial SEIR parameters. And my cat wants to, oops, call 03. Cat wants to come in. Okay, RST, and we'll run the program again, and in another hour we'll get an answer with social distancing and focus especially on what happens to those exposed and infected populations with this reduced contact in our population. Now another 55 minutes have passed, and I've completed the simulation with social distancing incorporated. Let's take a look at the results, starting with susceptible. Recall 01. Look at that. 74% of the population is still susceptible, compared with, as I remember, about 24% without social distancing. Now we'll go to exposed. Recall 02. 11.5% exposed. 3.6% infected. Compare that with about 25% and 10% with no social distancing. By just a 20% decrease in contact, there's almost a threefold decrease in the number of infected cases, or in this case, the proportion of infected cases in the population. And then 10.6% that are recovered, compared with about 40.6%, as I remember, from the simulation without social distancing. This is fantastic. This is the same result that I got with my 35S. It's much slower, but you can do it even on this ancient TI programmable calculator that will run for years on 2 button cell batteries. I'll be reviewing both the TI-66 and the 35S in future videos. I hope this was informative, and the source code in AOS is included in the description below. Please like and subscribe, and thank you all for watching.